Today I will talk about the 18 and 16 electron rules. Then I will talk about the D6, D8 and D10 complexes and their structures. I will talk about the ligands, pi-accepting ligands, sigma-donating ligands and pi-donating ligands, which is a new concept for us. And I will compare the NR3 and PR3 ligands by using the LUMO theory. And finally, I will show effect of electronegative atoms on PR3 ligands. And I think we can start with the 18 electron rule. And it is generally valid for the octahedral complexes. And if we look at an octahedral complex MO diagram, we have ligand orbitals and we have 6 of them if it is a sigma donating ligand. And we have also orbitals for the metal center. So we have the electrons, we have 5d electrons, we have an s electron and we have a p electron. So this is s, this is p, and this is the electrons of the metal center. And these electrons, so the orbitals split and causes an octahedral splitting. So this is the octahedral splitting. And we have T2G orbitals here and we have EG orbitals here. So these are the anti-bonding orbitals. And energy of S and P MOs increase a little bit. And all of these are also anti-bonding. T2G orbitals are slightly bonding or non-bonding, so we can consider them as a non-bonding. And ligand orbitals destabilize in the MO diagram, which is our driving force actually. So if all ligands have the electrons, so electrons goes to here, right? Then in this case we have 6 times 2 ligand orbitals. So EG orbitals, as I mentioned, is anti-bonding orbital. So if electron or electrons goes to the EG orbital, then it causes instability on the molecule. So we will consider to fill all the T2G orbitals, which means that 2 times 3 electrons. And if we make the calculation, we will find the 18 electron rule. So these electrons is coming from the T2G, and these electrons are the ligand electrons. And 18 electron is more significant for the strong field ligands, and these strong field ligands are, as you know, pi-accepting ligands. And these ligands, as I mentioned in my previous videos, are CN and CO. So what happens in the octahedral splitting? EG orbitals destabilized, so their energy increased a little bit, and T2G orbitals will not affected energetically, so they are non-bonding orbitals. By the way, we have to know that all ligands has a sigma donation ability. But CN and CO ligands has stronger back-bonding ability, and this causes the higher octahedral splitting. When the splitting is high, then EG orbital energy will increase, and increasing this energy will be destabilize the molecule if we exceed the 18 electron. And therefore, pi-accepting ligands generally prefer to occurrence of 18 electron complexes. However, we have different complexes. For instance, we have Ml4 complexes. And these complexes can have tetrahedral or square planar geometry. Firstly, I want to consider the octahedral geometry. So we have EG orbitals and we have T2G orbitals here. So in Ml4 type ligands are not approaching from XY and Z axis, and generally interaction between ligands and the metallic orbital is very low. So in this case, the x square minus y square will be very anti-bonding. So this is important. The x square minus y square orbital will be anti-bonding, and it will stabilize the dxy orbital and dz square actually. So dz square orbital will be stabilized, and we will have other d orbitals, the yz, the xz, and the xz. And these orbitals, all of these orbitals, are non-bonding. They can be considered as non-bonding. So square planar splitting is actually here. So if you put the electrons in the square planar complex to the x minus y square orbital, then we will cause a destabilization. The main difference between octahedral and the square planar complex is that we remove two ligands which stabilize the Z component. And if we fill the orbitals, and of course we have ligand orbitals, and ligand orbitals will be stabilized, and they will completely fill the molecular orbitals. We will have 8 more electrons for the non-bonding. So in this case, 8 electrons is coming from the metal center, and plus we have 4 times 2, which is comes from the ligand. We need 18 electron. So this not 18, this, we have 16 electron. So we have 16 electron rule for the square planar complexes. So generally, the 8 systems, which is this one, has square planar geometry. We have also D10 complexes. The issue in the D10 complexes, ligands donates the electron, but the metal center does not need electron, and therefore D10 systems generally prefer the tetrahedral geometry or TD. And the splitting of tetrahedral complexes is this. So we have T2G orbitals and we have EG orbitals. And the splitting for tetrahedral complexes is very low. And again we have ligand orbitals, which is completely filled. And D10 complex, of course, completely filled. Therefore it is D10. So 5 times 2 comes from the metallic center, and we have 4 ligands. It causes the occurrence of again 18 electron rule. So tetrahedral complexes can occur for the D10 systems, and the splitting is very low. Therefore all complexes are at high spin. Well, as I mentioned in my previous video, we have pi accepting ligands, we have sigma donating ligands, and we have pi donating ligands. So this pi donating ligand is new for us. I mentioned them in my previous videos, but you might be familiar with the pi accepting and sigma donating ligands. So firstly, pi accepting ligand, we need two important things. So we should have only one non-link electron pair, and we need a pi bond. Why we need pi bond? Since there should be a LUMO orbital and we need a pi star anti-bonding orbital to make the ligand a pi accepting ligand. Therefore we need also a pi bond. And you know this ligand, probably it is CO. We have non-bonding electrons and we have also pi bonds. So CO is a pi accepting ligand, and also cyan or cyanides is also a pi acceptor. And we saw pi-backdoantion ability of these two ligands. And the other important thing is that we must have low LUMO levels to interact the metal orbitals, which is another important point. So this is the pi accepting ligand, and we have also sigma donating ligands. And sigma donating ligands, we only one non-bonding electron pair, or we just a pi bond or a sigma bond. So sigma donation ability is very easy to understand, since we have a orbitals on the metal center, and a ligand, if it has a lone pair, it can donate its electrons. So again we can write, we should have one non-bonding electron pair, or we just need a pi bond, or we need a sigma bond. I want to explain these two. So an alkene, for instance, has a pi bond, and this pi bond can interact with the orbital of the metal and makes a bond. So this R group is a sigma donating ligand. The other possibility is, for instance, hydrogen. Hydrogen molecule has a sigma bond, and this sigma bond can interact with the metal center, and H2 molecule becomes a sigma donating ligand. The other important thing is that LUMO level of the sigma donating ligand should be high enough. In this case, it will not accept the electrons. And the last ligand type is pi donating ligand. And pi donation can appear if we have more than one electron pair. So simply we need to have more than one electron pair. So what is the interaction? As you know, we have the orbitals of the metal center, and a ligand becomes a sigma donor if it donates its one pair of electrons. In other case, so in this case, we have another orbital, and this orbital has electrons, and these electrons can interact with the other d orbitals of the metal center, which causes a pi donation from ligand to metal. So we need definitely more than one electron pair, and these molecules is, for instance, Cl minus, fluorine, or iodine, or OH minus group. We have more than one electron pair, which makes these ligands pi-donating ligands. And we can look at the pi-donating ligands MO diagram. So we have the orbitals of the metal center. We have an s orbital, and for instance we have a p orbitals. These two will not interact in the octahedral splitting, but the orbitals again will split as Eg and T2G. So we have sigma donating and pi donating ligands. So this is pi donation, and this is for the sigma donation. So sigma donation appears with the between the Eg and T2G orbital, and pi donation appears between T2G and pi orbitals. So we have two donation ability, which causes to decrease on the orbital energy. So Eg orbital will be filled by the pi donor, but if this wasn't the case, so the energy of these orbitals will be a little bit higher. So the splitting energy will be smaller for the pi donating. So pi donor, so pi donation will interact with the T2G orbitals, and sigma donation will be between the Eg orbitals. Or we can write in this form: sigma donation will affect the Eg orbital energy, and pi donation will affect the T2G orbital energy. So there will be electron transfer to the metal center, and electron density on metal increases, which destabilizes the Eg and T2G orbitals. So in this case, splitting energy will be very low, and therefore in pi donating ligands we generally observe a weak field ligands. So pi donor ligands are weak field ligands. And this is another important information. So if you consider the spectrochemical series, we firstly have pi accepting ligands, and these ligands are generally strong field ligands. We can consider them as NO plus, and CO, and Cn minus. Then we have sigma donating ligands, which is, for instance, NH3 and pH3, and I will talk about these two in a minute. And we have pi donating ligands, which is new for us, which is the Cl minus, fluorine minus, iodine minus, maybe water, since water has two lone pairs, so it might be a pi donating ligand. So these ligands are weak field, so they cause to low octahedral splitting, but pi-accepting ligands are strong field ligands. And they will cause higher octahedral splitting. And I want to make an example for the geometry. For instance, we have nickel CN4 2- complex, and we have nickel CO4 complex. So in here, nickel has D0 system, so it is natural, so we have a D10 system, sorry. And in here, nickel is 2 plus, so we have D8. So if you want to predict the geometry, we can easily understand that this is a square planar complex and this is the tetrahedral complex. So we can draw the molecule. So we have nickel on the center, we have one cyan here, we have another cyan here, and other two cyan molecule is coming to us. So this is the geometry of the square planar, right? And we can also make the MO diagram of this ligand. So we will have energy for the metal center. We have splitting. So this is definitely anti-bonding orbital, and we have other metallic orbitals. So this is the square planar splitting, and these electrons or these orbitals are non-bonding and they will completely filled. So we have I guess I wrote 1, 2, 3, 4, 5. Yes, I made a small mistake. So this is the x square minus y square. This is the splitting energy, and we have 8 electrons for this complex. So this is the simplest MO diagram for the square planar complex. So I just wanted to write here. And if you look at the other example, as you remember, the D10 system is completely filled, and we will have a tetrahedral splitting. Splitting energy will be very small. So these are the T2G orbitals and these are the EG orbitals. And all of them is full, right? And CO ligands can be put it here. And they are also fully filled. So we expect to see a tetrahedral geometry for nickel CO4. And we expect to see a square planar for this complex. So I want to compare the ammonia and phosphino ligands. For instance, we have a ammonia or NR3, not ammonia. I want to use the NR3 and PR3. Okay, so I want to compare their MO diagram. So again, we have an energy bar. We have 3 nitrogen 2p orbitals, but nitrogen is more electronegative than the p, so that energy of the p orbitals for the 3p should be a little bit higher. and we will have sigma star and bonding, right? And we have 2p of the R group. So I cannot use the S, therefore I want to compare with the PR3 and NR3. And we have to consider a HOMO. So we have electrons on the N, and these are the non-bondings. So these are our HOMO orbital. And again, we can look at the energy of the phosphinoligand. So we have again a LUMO, but the important point is that LUMO of the PR3 should be lower energy than the NR3. So NR3 energy is higher, and pi-backdoantion is hard, right? Since LUMO energy is high. And if you want to put the electrons here, it is not easy since LUMO energy is high. So that metal to NR3 ligand electron donation is hard for this case since LUMO energy is high. But here in PR3 case, again we have a HOMO energy, HOMO electrons. We have sigma, we have sigma star. These are fields. These are filled in both cases. But the main difference is LUMO energies. So I want to show the difference between these two molecules. So LUMO in PR3 is low and they can accept electrons. And I want to talk about the effect of electronegative atom on LUMO orbitals for the PR3. So firstly, we can consider the pH 3. In this case, we have carbon atoms and we have 3p atoms here for the P3p, and for instance I want to increase the electronegativity by adding oxygen, and also I can add fluorine to make it more electronegative. So in this case, what will happen is that fluorine is very electronegative, and fluorine atoms orbitals will be very low energy, right? So that pi star orbital or the LUMO orbital is very low. So this is LUMO of the PF3, and it is accessible for the metals. Then we have oxygen, and oxygen energy levels are a little bit higher, okay, and it can interact with the P3p orbitals, so they can interact with each other, and this energy will be higher than this bond, but it causes the increase of the LUMO energy. Of course, LUMO of the sigma star, so sigma star will be higher. These are the sigma star orbitals, so energy will be increased. So LUMO will not be very available for the metals, so that adding electrons to these orbitals will not be very easy. And in PPH3, carbon, so this is carbon, and this is the oxygen orbitals. In carbon case, it will be worse, since the interaction between these orbitals will be higher, maybe something like this, and therefore this energy will increase more, right? So LUMO energy will increase for PPH3 molecules. So this is the sigma star, and it has higher LUMO energy. So the question is, which one is the best pi accepting ligand? So which can accept the electrons? Definitely PF3 can accept the electrons easily. So actually PF3 is a pi accepting ligand. Due to low LUMO energy level. So I want to draw the interaction between the PR3 ligand and the metal center. For instance, we have ligand on the metal and we have a PR3 group. So firstly, it can donate its electrons, right? We have electrons here. We have, for instance, a d electrons, d orbitals on the metal center. It can donate the electrons. But if there is a LUMO level which is available for the metal center, the metal can donate its electrons to the phosphine ligands. And again, this is pi-backdoantion. So this green thing, maybe I can make it green. So this is pi-backdoanation, and we can experimentally prove it by using infrared or XRD. So XRD data can be used to determine the bond length or bond distance between the P and metal center. And for instance, we have a PR3, okay, and maybe we have PR2F. So this has a pi accepting ability, and if it accepts the electrons, then metal and P bond distance can change, and this change can be detected by using the XRD, and we can prove that this PR3 can accept the electrons from the metal centers. And we can simplify the LUMO diagram for this case. For instance, we have a phosphino, so we have P here, and we have I want to visualize the PR bond, so I want to delete here. So we have a P, okay. We have, for instance, carbon. We have nitrogen. Nitrogen is more electronegative. So we have oxygen, and we have fluorine. So this is a little bit off maybe, but these two can interact, right? And it can create a sigma bond, and it can create a sigma star. But this sigma star will have very low energy. Oh, sorry, it will not be in low energy, it will have very high energy. So interaction will be high. So this is the sigma star for the carbon case, and I want to make the nitrogen red, okay. So in nitrogen case, this will be sigma, but sigma star will have lower energy than the carbon. So this is the sigma star. And we have oxygen. I want to make it green. Okay, carbon is black. Carbon is black. Oxygen is green. And oxygen sigma star will be here. So its energy, or the LUMO, these are LUMO of course, will be lower, and oxygen pi star pi will be at the lower energy level. And maybe we can add the fluorine, hopefully. And fluorine will be lower energy, and it will be best pi accepting ligand. So this is the PR bond. Okay. So I want to make a very simple example. For instance, we have nickel carbon 4 and we want to add PPH3. Okay. So this reaction is very possible, and I want to compare the carbon stretch for complex 1 and 2. This is complex 1 and this is the complex 2. What we know. So PPH3 can donate the electrons, so it's a sigma donor. It is not PF3. If it is a PF3, it might behave like a pi accepting ligand, but it is not the case. So what will happen is that if we add the one of PPH3, there will be electron donation to the metal center. So electron donation will happen, but the electron donation from the metal center to PPH3 is not possible, or it's unlikely. And on the other hand, we have a CO groups. This part is more important. And CO will have pi-back donation ability, right? If the metal center is more electron rich, then CO back donation will increase. If the back donation increases, then the CO bond strength will decrease, and VCO stretching also decreases. So this is from the combination of my previous lecture and information about the PPH3 ligands. So we can say that simply for the VCO1 should be bigger than the VCO2, since there is a back bonding here. It will accept more electrons from the metal center. It will decrease the CO strength and it decreases the VCO. Therefore, VCO1 should be bigger than the VCO2.